Welcome everyone to today's Masterclass Explainer. I'm absolutely thrilled to have you here. Today, we're going to tackle something really beautiful. We are going to translate the dense, elegant mathematics of electromagnetic radiation into physical reality. Specifically, we're unpacking Chapter 2, Section 2.3 of our text, Radiation from a Short Current Filament. So settle in. We are going to break down these formulas step by step, so you don't just memorize them, but you truly, deeply understand why they work. Before we get bogged down in a complex calculus and field equations, let's establish our core question. The foundational mystery we are solving today is this. How exactly does a simple, theoretical, infinitesimal sliver of wire carrying an alternating current push energy out into the vastness of space? How do we get from a tiny wire to the massive web of radio waves that connect our entire modern world?
All right, here's our roadmap for today. 1. The postulate. 2. The mathematical framework. 3. The derivation. 4. The physical reality. And 5. The practical application. Let's dive right in.
Section 1. The postulate. Defining the physical model.
In engineering, we always start by simplifying our model to its absolute most fundamental components before we tackle the messy complexities of reality. We place an infinitely thin current filament, which we'll call length dl, precisely at the origin of our axes, and we orient it straight up along the z-axis. Now, because radiation spreads outward in all directions, trying to map its effects using a standard Cartesian XYZ grid would just be a total nightmare. So instead, we use a spherical coordinate system. We rely on the radius r, the polar angle theta, and the azimuth angle phi.
We really need to rigorously define what this element is. A short current filament is a completely theoretical antenna element of infinitesimal length, dl, and an infinitely small cross-sectional area. Most importantly, we assume a perfectly uniform current I across its entire length. Now you might be thinking, wait a minute, a uniform current on an open-ended wire? That's physically impossible. And you'd be absolutely right. But we construct this theoretical filament because its absolute mathematical simplicity makes it the perfect building block. It's a differential element for understanding and calculating all the complex real-world antennas we'll encounter later on.
Moving on to Section 2, the mathematical framework, unlocking the vector potential.
Okay, we need to establish the governing equations that describe exactly how the electromagnetic fields propagate away from this tiny source. Our textbook methodically lays out a three-step mathematical attack plan. We don't just jump straight to the electric and magnetic fields. First, we solve for an intermediate mathematical construct called the vector potential, which we denote as A. Once we have A, it acts like a master key. We take the curl of A to unlock the magnetic intensity, H, and from H, we can easily determine the electric field, E.
So the crucial starting point here is equation 2.24, which gives us the final solution for the vector potential. It reads, A equals mu naught times I times dl divided by 4 pi r, all multiplied by e to the negative j k naught r in the az direction. Notice that because our current is flowing entirely in the z direction, our vector potential is also completely in the z direction.
Let's deconstruct that formula a bit so you can truly see the physics hiding within the math. The mu naught ideal part. That's just the source strength. But look at the 1 over r in the denominator. That reveals that the wave's amplitude inevitably dilutes as it spreads outwards. It's inversely proportional to distance. And that complex exponential term e to the negative j k naught r, that beautifully captures the phase delay. It is literally the mathematical heartbeat of a wave propagating outward through space and time at the speed of light.
Section 3. The derivation, isolating the far zone radiation fields. We now transition from the immediate, highly reactive space surrounding the wire, what we call the near field, into the simplified, propagating physics of the far zone. If you look at the full textbook equations for E and H, they're quite messy. They contain 1 over r squared, and even 1 over r cubed terms. But here's where we apply the far zone limit. When we move far away from the antenna, many wavelengths distant, the complex higher-order fractions, like 1 over r squared, drop off to near zero. We are left only with the dominant 1 over r terms. These are the only terms that actually radiate real power into space.
Applying this far zone limit yields these incredibly elegant expressions for the electric and magnetic fields, equations 2.29a and b. The electric field is E equals J times Z naught times I times dl times k naught sine theta all over 4 pi r multiplied by e to the negative j k naught r in the a theta direction. And h is very similar but lacks the z naught and is in the a phi direction. Notice how the vector components have shifted. We no longer have z components. The electric field is entirely in the theta direction, and the magnetic field is entirely in the phi direction.
And this brilliantly illustrates a universal truth of electromagnetic radiation. Out in the far zone, the E and H fields are always locked strictly perpendicular to each other, and both are perpendicular to the direction of travel, the radius vector. They propagate outward as a transverse wave. Furthermore, if you simply divide the magnitude of E by H, you get Z0. That's the intrinsic impedance of free space, which is exactly 120 pi ohms, or roughly 377 ohms. The math perfectly dictates the physical structure of the wave.
Section 4. The physical reality, power, directivity, and patterns.
So, where's all this power actually going? Well, it absolutely does not radiate in a perfect sphere. It actually forms a three-dimensional donut shape, a toroid. If you place the wire vertically along the z-axis, the radiation puffs out predominantly to the sides. Why a donut, you ask? Well, think back to our far zone equations. Both E and H contain a sine theta multiplier. Because of that sine theta term, if you look straight down the top of the wire where theta is 0, sine of 0 is 0. You get absolutely no signal. The whole of the donut is completely dark to radiation. But at the equator, perpendicular to the wire where theta is pi over 2, the sine is 1, and you get the maximum possible blast of electromagnetic energy. This directional bias is quantified by a vital antenna metric called directivity. For our short filament, the directivity is 1.5 times sine squared theta. This tells us that in its absolute optimal direction straight out from the side, this simple filament focuses power 1.5 times more effectively than a theoretical isotropic antenna that just radiates equally everywhere. It intrinsically shapes the power. Section 5. The practical application, radiation resistance in practice.
Now, to bridge this high-level physics to real-world circuit design, we use the concept of radiation resistance, shown here in equation 239. This formula, R sub A equals 80 pi squared times the quantity dl over lambda naught squared, is profound. It allows us to model the power radiated away into space simply as a standard circuit resistor. And notice the key dependency here. It is entirely dependent on the ratio of the antenna's physical length, dl, to the wavelength of the signal, lambda naught.
The text sets up a fantastic, slightly humorous scenario to prove a point here. Imagine we try to broadcast a standard AM radio signal at 1 megahertz. At 1 megahertz, the wavelength is roughly 300 meters. Now suppose we try to use a puny 1 meter long wire as our antenna. Our del L is 1 and our lambda is 300.
Let's do the math on that. 1 divided by 300. Square that tiny fraction and multiply by 80 pi squared. Plugging those numbers in gives us a shockingly dismal radiation resistance of just 0.0084 ohms. Think about what that number means practically for engineering. Because that radiation resistance is so infinitesimally small, less than 1/100th of an ohm, it acts almost like a short circuit. The natural resistance of the copper wire itself will actually be higher. Thus, almost all your expensive transmitter power will just burn up as heat in the wire, that's ohmic loss, rather than radiating out into space. This math perfectly explains why AM radio stations operating at long wavelengths simply cannot use small antennas. They are mathematically forced to build those colossal, towering structures you see out on the horizon.
And that brings us to the end of today's derivation, but it leaves us with an incredibly tantalizing engineering mystery for our next session. We've just mathematically proven why short antennas utterly fail at long wavelengths. Yet, we all carry cell phones with tiny antennas communicating at relatively long wavelengths. How on earth do engineers overcome this strict mathematical limit to make the highly efficient, compact communication devices we use every single day? Think on that. Review your derivations, and I will see you all in the next masterclass.